Have you ever seen a brilliant streak of light dash across the night sky? That momentary flash that leaves you wondering what just happened. These spectacular events are often bolides, extremely bright meteors burning up as they enter Earth's atmosphere. But what happens after the light show ends? Where do these space rocks go? It turns out that the same technology that helps meteorologists predict tomorrow's weather is also tracking these cosmic visitors as they fall to Earth. According to NASA researchers Mark and Jeffrey Fries, weather radar systems are proving to be invaluable tools for finding meteorites before they even hit the ground. Weather radar networks like NEXRAD were designed to detect raindrops, snow, and other atmospheric particles. These systems constantly sweep the skies, sending out radio waves that bounce off various objects and return valuable data about what's happening in our atmosphere. They're sensitive enough to track migrating birds and even bats flying at night. What scientists have discovered is that these same radar systems can detect meteorites during what's called their dark flight phase. You see, when a meteor first enters our atmosphere, it's traveling at incredible speeds, tens of thousands of miles per hour. This generates intense friction, heating the object and creating that brilliant streak of light we associate with shooting stars. But something interesting happens as the meteor slows down. Eventually, it cools enough to stop glowing, becoming virtually invisible to the naked eye. Yet it's still falling, potentially for several more minutes, as a dark object. This is where weather radars come into play. They can see these fragments, even when our eyes cannot. What makes this particularly valuable is that these radar systems operate 24 hours a day, 7 days a week. Unlike visual observations that are limited to clear night skies, radar can detect falling meteorites in broad daylight, through clouds, or during stormy conditions. By analyzing radar returns, scientists can calculate exactly where meteorites are likely to land, creating what they call a strewn field, the area where fragments of various sizes scatter across the landscape. This information is combined with wind data from weather balloons to create precise maps for meteorite hunters. The results can be impressive. During the 2003 Park Forest meteorite event near Chicago, weather radar data guided search efforts that led to successful recoveries of numerous fragments. These recovered samples provided valuable insights into asteroid collisions and how meteors break apart as they enter our atmosphere. Of course, distinguishing meteorite signals from other radar returns isn't always straightforward. Weather radars detect everything from birds and insects to dust particles. Scientists look for specific characteristics that set meteorite falls apart, such as brief, strong signals appearing high above ground level and away from typical rain clouds. For daytime events when there's no visible streak in the sky, researchers might rely on infrasound detections or eyewitness accounts to confirm that a meteor fall has occurred. They can then check radar archives to pinpoint potential landing sites. What makes this approach particularly effective in the United States is the open access nature of radar data from the National Oceanic and Atmospheric Administration. This allows for quick searches when an unexpected event occurs. Similar radar networks exist around the world, offering the potential for global meteorite tracking if data sharing protocols are established. But why does any of this matter? Each meteorite recovered is a pristine sample from space, a fragment of an asteroid or comet that formed during the early days of our solar system. Some may contain organic compounds, while others preserve evidence of ancient cosmic collisions. When scientists can retrieve these specimens quickly, before they're contaminated by Earth's environment, the scientific value increases dramatically. The technology continues to evolve. Machine learning algorithms may soon help separate meteorite signals from normal radar noise more efficiently. As more bolides are recorded and meteorites recovered, patterns will emerge that could allow software to automatically flag potential meteorite falls as they happen in real time. Different countries use radar systems operating at various frequencies, S-band, C-band or X-band, each with advantages for detecting fragments of different sizes. A coordinated global approach could create a comprehensive network for tracking these cosmic visitors wherever they land. Organizations like the American Meteor Society already gather eyewitness accounts of fireballs. When combined with radar data, these reports can guide volunteers to search areas within hours of a fall. People living near these landing sites often have no idea that valuable space rocks have just landed in their vicinity. Timely maps can lead to swift recoveries of scientifically important specimens. The more meteorites we collect, the closer we get to answering fundamental questions about our planet and solar system. Each new specimen helps scientists assemble a clearer picture of the objects that share our cosmic neighborhood. So the next time you spot a brilliant streak across the sky, remember, beyond that momentary light show, weather radars around the world may be tracking the final journey of a visitor from space. Long after the glow fades, these systems continue watching, helping scientists recover precious messengers from the cosmos that might otherwise be lost forever. And with every meteorite recovered, we gain new insights into where we came from and our place in the universe. For more on this story, find a link to the article on Earth.com in the description.